Hello, this is Mrs. Schroeder. We have been talking about systems at equilibrium, and now we're going to start talking about systems at equilibrium when they involve a salt. And we're going to use this KSP expression when we talk about the solubility of slightly soluble salts. So the solubility product constant KSP talks about how much of a salt will actually be in solution. Up until now we had either soluble or insoluble for salts, but really all things that we've called insoluble, there's a slight solubility, a little bit of dissociation that occurs even when we've said it's insoluble. It's just so small that it's insignificant. An example of this, when calcium fluoride is put into a solution, we have this equilibrium happening when I have some calcium ions and some fluorine ions that are forming in the solution. And I'll show you how to do those dissociation reactions in class. But KSP is the constant. Once we know how to do a dissociation reaction, writing them out with the ions, we're going to make our equilibrium expression the same as we did where we have products divided by reactants, and we're going to use the coefficients as the powers. So this one was the CaF2 when it went to Ca2 plus F, there's two F minuses, so the 2 becomes the power here, and I have Ca and F. And if this was measured at 25 degrees Celsius, it would be 1.6 times 10 to the negative 10th. That's a very low number. So this is why it's considered an insoluble salt, because it is such a low number, but there is a slight solubility to it. And this is true whether I take some CaF and I just dump it in water, or if I have it in a solution that already has calcium from something else in there. This relationship with calcium times the fluorine squared will apply no matter where the ions came from. So some solubility constants, again, for slightly soluble salts, range anywhere from 10 to the negative 49th, negative 10th, negative 33, negative 5th. So I have all sorts of different ranges. These are all, again, very, very low numbers. So make sure you write this down in your notebook, because we're going to be using this. First, I have to start with a balanced chemical reaction. This is the dissociation equation of the salt. When you put a salt in water, you have the solid and it turns into its ions. They're always written so the solid salt is the reactant and the ions are the products. You're going to write your KSP expression. The solubility product constant expression is the KSP expression. You're going to complete it by putting any powers in that you need. And then you're going to figure out the concentration of the ions. You can use the amount that was put in of the salt to figure out concentration of each ion. If you have 2 of something, you may need to use mole ratios. If you know you have, like for the fluorine, there were 2 fluorine ions. So consider that times 2 when you're trying to figure out the concentration. Example here, silver bromide. Slightly soluble. It has a solubility of 2.3 times 10 to the negative 7th molar. Calculate the solubility constant for AgBr. I start with my balanced equation. AgBr goes to Ag plus Br minus, and both of these are aqueous. Well, this was my solid. Write my solubility product constant expression is my KSP. It's going to be equal to the concentration of Ag plus times the concentration of Br minus. Figure out the concentration of the ions. And this is going to be based on what did I already know? Well, I already knew that this was 2.3. The solubility is 2.3 times 10 to the negative 7th. So if this is 2.3, this one and this one will all have to be equal. The Ag and the Br have to be equal. And they're going to have to both equal that number because that's the solubility and it's a 1-to-1 ratio. And I'll show you this 2.3 times 10 to the negative 7th, AgBr, just like we did in stoichiometry, where we had 1 Ag plus for every 1 AgBr. So I still get the same number, 2.3 times 10 to the negative 7th for both of those. So I'm going to use those in my expression. 2.3 times 10 to the negative 7th times 2.3 times 10 to the negative 7th. And you could use that and call it squared instead of writing it out this way. So 2.3 times 10 to the negative 7th, and I'm going to square that number. And that equals 5.29 times 10 to the negative 14. Okay, this is how I would do the sample problem. I can do this one for you in class tomorrow. We'll do a couple more practice problems in class, but we can also go backwards with our equations. Sometimes we know what the KSP is, but we want to know what the ion concentration is. Or sometimes we know one ion, but not the other one. So we may have to go backwards with this. So I can do this backwards if I have copper chloride, and this is my solid, and it goes to Cu plus Cl minus, aqueous. I know the KSP expression would be Cu plus times Cl minus, and KSP is 1.2 times 10 to the negative 6th, because the constant equals that. And that's going to equal my Cu and my Cl. It told me that chlorine is this. I'm putting into salt in the ocean. The ocean water has other things in it. It has Cl from other sources, like magnesium chloride, sodium chloride. So I would leave the Cu as my unknown, but in this case these two don't equal each other because their chlorine is coming from other places. And it's coming from other places to the 0.55 is its concentration. So when I solve for copper, the concentration of copper ions, I take the 1.2 divided by 0.55, and I get 2.18 times 10 to the negative 6th. So that's the concentration of the copper ions in this solution. So again, we have some more problems to practice, and we'll do some of these in class, learning how to find solubility of a salt, a slightly soluble salt.